Okay, so thank you for coming to another edition of Quantum Computation and Isolation. So today we have Peter Johnson giving today's talk. So Peter got his BA in physics from Kenyon College in 2010, his PhD in physics at Dartmouth College under Professor Lorenzo Viola in 2016. He was then a postdoc at Harvard University from 2016 to 2018 under Professor Alan Asparuh-Kuzik, and he then went on to co-found Zapata Computing along with other researchers from Asparuh-Kuzik's group, and currently works there as a lead research scientist developing quantum algorithms and software. And today he'll be talking about some of the work that he's been doing there. So please help me in welcoming either by unmuting yourselves and clapping or by clapping virtually, Dr. Peter Johnson.
Thank you, Josh, for the kind introduction. Yeah, and again, please feel free to interrupt throughout. I would say the more questions, the better. So let me share my screen. And maybe a thumbs up if you can, you're able to see the slides. Okay, great. Okay, so I will be telling you all about some recent work that we have published. And for those of you in quantum computing, my goal is to introduce you to a tool that we've been developing, which might be useful in your research. And for those of you outside of quantum computing, I hope that this will give you a sense of the interesting problems that are trying to be solved in the field these days. Okay, so yeah, let me just start by acknowledging the researchers at Zapata who I worked with. So Guoming Wang, who's a research scientist at Zapata, Dax Ko, who was a postdoc with us, but has since moved to A-Star in Singapore, myself, and then one of the other Zapata co-founders, Yu Dong. So yeah, this was a very fun project, and it stemmed out of, as you'll see, out of a pretty dark place that we were in. And you can find more details on the work I'll be talking about in a recent PRX Quantum article that we published, as well as an archive preprint on like a particular aspect of this work. Okay, so I want to set the scene or give the context that we were in as we started to embark on this work. So at Zapata, we're pretty focused on trying to develop ways to make quantum computers useful as soon as possible. And so a lot of this ends up focusing on today's quantum computers, like the one that the Google group achieved quantum supremacy with. But actually for this work, our focus was on more future quantum computers, those that we expect to be the first to achieve quantum advantage. And the questions that we were asking were, picturing this device, what might we ask this future quantum computer to do? What type of device is best suited to do that task? And more specifically, will this quantum advantage machine use this standard VQE, a cornerstone of these near-term quantum algorithms? So yeah, I just want to put everyone in the right mindset where we're thinking about the moment where quantum computers solve useful problems rather than trying to just improve today's quantum computers. And so what do I mean when I'm talking about today's quantum computers? So as you might know, right, Google, IBM, Rigetti, Honeywell, IonQ, many others are actively developing quantum computers. These quantum computers have on the order of single to double digits of physical qubits. And so far, they have not solved any problems of practical relevance for industry. And so, the quantum advantage machine could be a future evolution of one of these devices, but certainly none of these devices are capable of solving the problems that we'll consider. So I also mentioned these quantum algorithms suited for these today's quantum computers. So we refer to these as near-term quantum algorithms. You might recognize some of these acronyms, including VQE and QAOA. Maybe those are the two most popular. So researchers over the last 5+ years have been trying to develop quantum algorithms that are tailored to the limitations of of today's quantum computers. And so these algorithms are characterized by their robustness to error. They tend to use fairly short quantum circuits, short depth quantum circuits, and they often require a heavy load on the classical computer, such as some kind of classical optimization. But one thing that is coming more to light is that a downside of these near-term quantum algorithms is that they're quite costly in terms of the time that they take to solve problems. And so to give some examples, a recent paper was put out by some folks at Los Alamos, pointing to some of the shortcomings in this variational quantum linear systems solver algorithm, and showing that it's quite expensive in the runtime it requires. Also recently, some work coming from Zapata carried out a pretty large-scale benchmark study for the VQE algorithm. And here too, the conclusion was a bit pessimistic, finding that VQE is very costly in terms of time for solving problems of industry relevance. So I am going to focus on the case of VQE. I guess I'll use VQE as a bit of a punching bag in order to motivate the algorithms that we were developing.
Peter?
Yeah, Lorenza, please.
Sorry for interrupting, you know me. You mentioned a few times problems of industry relevance.
Yeah.
Can you expand a little bit on what constitutes in this vision like an industry relevant problem, and why wouldn't like something for just science relevance be under the purview of this?
Yeah, maybe the first thing I'll say is that I think under the science purview, I think we should be considering these problems as well. I think the reason I'm referring to these industry problems is that the projects that we're doing at Zapata are with companies that are interested in using quantum computing in the future. And so, the nature of the problems that we end up considering are of industry relevance.
And
I think,
you're going to say a bit more on that type of problems that that fall in this category?
Yeah, so let me use VQE as the example and like go into a little more detail about this this specific project. And I think this can give some a better perspective on like what the types of problems are. So maybe it's as if you like anticipated my next few slides. Okay, so I am going to spend some time talking about the variational quantum Eigensolver algorithm, and yeah, Lorenza, I'll talk about some of the specific problems that we considered. So why would industry care about the variational quantum Eigensolver? So this can be used to predict properties of molecules, such as binding strengths, reaction rates, and molecular pathways. And at its core, it's solving the problem of estimating the ground state energy of a Hamiltonian. In this case, we'll consider a molecular Hamiltonian. So I'm going to go a bit into detail about this particular project. I'll talk about the problems that they benchmarked. And this will reveal the conclusion that VQE is too slow for the problems they considered. So yeah, this is the VQE algorithm has been implemented in a number of high-profile publications by IBM, Google, and however, these were all done on fairly small quantum computers, in the single digits of number of qubits. But what we are expecting that the hardware will grow over the next 5 years. I think many people might have seen these pretty aggressive roadmaps put forward by hardware companies. So question we ask is, what hope do we have for VQE to be solving problems on these future larger devices? So while there's been a lot of advance on the hardware, in parallel, there's been a lot of improvement in terms of the algorithm itself. And so we like to think of this as like a VQE pie, and a lot of work at Zapata has gone into improving these individual components of the algorithm. And so this brings us to the question of, like, with all of these improvements, is there hope of using the quantum advantage machine with standard VQE? So let me get into this benchmarking paper that I referenced earlier. So the conclusion of this work was, for the problem instances they considered, the VQE algorithm does not stand to outperform the classical state-of-the-art methods. And so what were these problem instances that they considered? So in the case of this project, we were interested in studying the combustion properties of these various molecules. So they picked a representative set of hydrocarbons, and they benchmarked the performance of determining their energies with state-of-the-art classical methods. And then they also carried out a resource estimate for the VQE algorithm. And so the findings were fairly pessimistic. So here is a table that summarizes the results. So you can see that for each molecule considered, it lists the number of electrons in that molecule, the number of qubits needed to represent that molecule on the quantum computer. And then the row, which is maybe most important here, is this bottom row. So this bottom row shows the time that it would take the quantum computer, the time that it would take running many samples from the quantum computer in order to gather enough samples to get an accurate estimate of the energy of the state that's prepared. And so you can see that, in some of these cases, let me pick a middle of the road one, it would take 18 days of running the VQE algorithm just to evaluate the energy of the state that's prepared. And so this evaluation of the energy is just a subroutine in the larger VQE algorithm. And so this 18 days would have to be carried out many, many times in order for the full VQE algorithm to run. So it was these numbers of multiple days for just energy evaluation in VQE, which led to this pessimistic conclusion. Yeah, it sounds like somebody might be asking a question.
Yeah, I wanted to ask a quick question. This is James Whitfield.
Hey, James.
Hey, Peter. So does this cost include the cost of doing the classical optimization? This seems like if you have to do many iterations, it might be much longer, right?
That's right. So maybe if you imagine that it would require like 100 iterations, you could add a multiple of 100 to these numbers.
This is just to evaluate one point.
This is just to evaluate one point, one energy. And evaluate that energy to within chemical accuracy. Okay. Yeah, thanks for the clarification. Okay, so why is VQE so slow at evaluating these energies? So in order to appreciate this, we'll get into how the algorithm itself works a bit. So VQE encodes wave functions of the molecules onto quantum states prepared on the quantum computer. This is done by a so-called ansatz circuit applied to some initial state. And the parameters of the ansatz circuit are tuned so as to minimize the expectation value of the energy of the state that's prepared. And once some convergence has been reached in terms of like a sufficiently, finding some minimum in the space of these parameters, this value is taken as a proxy of the ground state energy. And by the variational principle, this energy will be in upper bound to the true ground state energy. So the way that this is carried out, James referred to the optimization loop in VQE, is that the quantum state is prepared and repeatedly prepared and measured. And through tomography, an estimate of the energy expectation is obtained. And this estimate is fed into a classical optimizer, which decides how to adjust the ansatz parameters for the subsequent quantum state preparation. And so this is this VQE optimization loop. And the component of this loop, which was responsible for these very long times, is just this very small subroutine, which is referred to as quantum expectation estimation. And so the way that this subroutine, so the goal of this subroutine is simply to estimate the expectation value of one term in the Hamiltonian. We'll call that term like HI. You could imagine that this is like a Pauli string. And so the goal is to estimate this Pauli expectation value. And so VQE uses a method that we refer to as standard sampling in order to estimate this quantity. And so it works very much like you would estimate the likelihood of heads of a coin, which is that you repeatedly draw samples, and the sample average is used as the estimate. Just like how if you flipped a coin 100 times and got 75 heads, you might estimate that the likelihood of heads is 75%. So this is a fundamental subroutine of the VQE algorithm. And as I'll explain, it is responsible for the slowness of the algorithm itself. So we can picture how this process of gaining information about this parameter occurs. So in this top plot, the horizontal axis corresponds to the various possible values for this parameter, while the vertical axis is our belief about the relative likelihoods of the parameter being different values. And so I just want to play a movie which shows over time, as we take more samples, how our beliefs about the true parameter will change. So hopefully you can see this video. So with each sample that's obtained, we update our beliefs about the relative likelihoods of the parameters. And on the bottom here, we have a plot of the precision, or basically the width of this peak shrinking as we take more and more samples. And so the profile of this, the narrowing of this peak follows the familiar 1/√n scaling. This is kind of like related to like a central limit theorem. And so it will be this 1/√n, which is responsible for the high number of samples required by the energy estimation in VQE, and therefore the very high run times. Okay. So this leads us to this maybe lesser known measurement problem. It's that VQE requires too many measurements to be practical for some problems. And because each measurement is taking some finite amount of time, the reduction in this, or the improvement in precision, follows a 1/√t profile. And so I want to point out that this is not just an issue for that's due to error on the quantum computer, but this scaling persists even if you're using an error-free quantum computer to estimate these energies with standard sampling. So yeah, just to emphasize, this has nothing to do with error on the quantum computer. It's error due to the statistical sampling. Okay. So is there any hope of changing this scaling to overcome this measurement problem? So yes, indeed. One of the oldest quantum algorithms is the quantum phase estimation algorithm. And this is able to carry out estimates which have a so-called Heisenberg scaling in the precision as a function of time. However, this comes at the cost of requiring very deep quantum circuits. And so we don't expect near-term devices to be able to implement this algorithm. So is there any hope for an in-between? Is there some way to achieve a scaling which compromises the precision and changes the required circuit depths? So yes, quite recently, some folks out of River Lane developed an algorithm that they call alpha VQE, where they introduce this scaling parameter, which alters both the circuit depth and the scaling in this precision versus time plot. And so this was the inspiration for a lot of the work that we continued to do in improving this measurement problem. So to give a brief history of where this came from, this work was inspired by two separate works, one on efficient Bayesian phase estimation, and also the operator estimation algorithm of Nil, Ortiz, and Soma. And these, in turn, were inspired by some work by Microsoft on faster phase estimation, And both of these were inspired by the Kitaev's quantum phase estimation algorithm. But this Bayesian thread is coming more from the maybe Hamiltonian characterization literature. And these are inspired by probably many works in quantum metrology, papers that, are an area that I'm not so familiar with. And so our work can be seen as combining insights from this alpha VQE work, along with some of this adaptive Hamiltonian estimation work, which incorporates the effect of error into these estimation algorithms. And also the fixed point Grover search and the following quantum signal processing techniques that came out of this work. So the approach that we were taking is, I would say, more of a bottom-up approach compared to this alpha VQE work. So we're thinking, given a noisy quantum device, how might we optimize the rate of information gain in carrying out this estimation task? And so the principles were to incorporate the effect of errors in the quantum computation in the design of the algorithm itself. And we were aiming to maximize the rate of information gain with the resources available, and also trying to design the quantum circuits that we use to be as trim as possible. So I want to introduce this technique that we've been developing in a fairly pedagogical fashion, starting from what was familiar from the VQE algorithm. But maybe at this point, since I've finished the motivation, I should pause and ask if there are any questions. Okay, well, yeah, maybe I'll reiterate then that the purpose of this work is to try to resolve this measurement problem that VQE and other near-term quantum algorithms suffer from. And we're drawing inspiration from some of these recent works. Okay, so I'll title this section, Enhancing Information Gain. So recall that in VQE, the way that the expectation values are estimated is the onsot state is prepared, and then the poly string is measured many times, and a sample average is used as the estimate of the expectation value. So the circuits that we use to generate these so-called enhanced samples is a simple variant of this standard sampling circuit. So after preparing the onsot state, we then apply the poly string as a gate itself. And then we effectively apply a reflection about the onsot state, which can be done by first inverting the onsots and then applying a reflection about the initial state, followed by the onsots itself. And so this pairing of two reflection operators, P and then this A, R, A, compose to create effectively a Grover iterate. And so the main unit we introduce is using these Grover iterates on top of the onsots preparation. And then this is followed by a measurement of the poly string, and we receive a binary outcome again. And so maybe I'll point out that compared to like phase estimation or amplitude estimation, this technique is not requiring the use of additional ancillas. So in that way, it's similar to standard sampling of VQE. And so the question, though, is with these measurement outcomes, how are we to infer the expectation value of interest from them? It's not clear that these measurement outcomes, that their relative rates correspond to something that you could just take a sample average with. So after taking many samples, how do we infer the true expectation value? So the tool that we use to do this is called the likelihood function. And the likelihood function will also reveal to us why this enhanced sampling method is more efficient in gaining information about the expectation value. So the likelihood function captures how likely the different outcomes are given the true expectation value. And so in the case of standard sampling, these two are just linearly related, which is what allowed us to take the sample average. In the case of enhanced sampling, the likelihood function is a little more complicated. And it takes the form of this cubic polynomial. And the reason why this enhanced sampling likelihood function is more informative is because for small changes in the parameter of interest, there is a larger change in the observed rates of the binary outcomes. So in this sense, the likelihood function is more sensitive to the parameter of interest. Maybe I'll point out that the form of this likelihood function is what's called a Chebyshev polynomial. These show up in the Grover algorithm and many modern quantum algorithms. And it's from the use of these Grover iterates. And so we refer to this as the Chebyshev likelihood function. Okay, so how are we actually how are we inferring these parameters based on the data that we're receiving from these measurement outcomes? So the tool that we use for this is Bayesian Inference. And so I'll just briefly introduce the inference process. So we start out with some prior beliefs about the true parameter. And upon receiving some data, we then use the likelihood function to update our prior beliefs. And this is done via Bayesian inference. So this is the Bayes rule. Effectively, you're multiplying the likelihood function to your prior. And this results in a posterior distribution, which is ideally more concentrated around the true parameter. So there are many ways that Bayesian inference can be carried out numerically, but this gives the theoretical concept that we use to infer the parameter of interest. So what happens when we do a direct comparison of using the standard sampling procedure to enhanced sampling? So we can run this same video that we had before, and we notice that with each sample, the enhanced sampling posterior concentrates more narrowly around the true parameter than does the standard sampling. So this can be captured with this mathematical quantity known as the Fischer Information. This describes a type of measure of information gain. And it can be thought of as expressing like the power of the likelihood function to inform you about the parameter of interest. And in a very rough sense, you can think that this is this should be related to the steepness of the likelihood function. A steeper likelihood function can be more informative of the parameter of interest. So if we plot the Fischer information versus the samples, we find that in the case of enhanced sampling, there's a 9 times improvement in information gain per sample. Of course, the circuits used in enhanced sampling are deeper, so this requires, in this case, a factor of 3 more time. And as we'll show, this leads to a linear improvement in the Fischer information per time as we use more of these Grover iterates. Okay, so lastly, I'd just like to talk about how we think about using this method in practice, because in practice, we have to take into account the fact that the quantum computers have some inherent error, and the algorithm itself is taking this into account to make better estimates. So we take a fairly simple model of the impact of device error on the likelihood function. So we imagine that with each additional Grover iterate that's applied, the likelihood function is attenuated by a constant factor, this e to the minus lambda. And so when carrying out inference, we will use this model of the noise. And in many cases, what we will do is also treat this decay parameter as another parameter that we infer, so that it can be so that we can also learn the effect of the noise as we're carrying out the algorithm. And so, okay, when we start incorporating noise into the algorithm, what do we expect? So as I said before, as we're using more and more of these Grover layers, we expect there to be a gain in Fischer information. And indeed, it should grow roughly as the number of layers squared. But there's a counteracting reduction in this Fischer information, which is decaying exponentially in L. And so we should expect there to be some balance to strike between these two competing factors. And so if we consider aiming to optimize the Fischer information per time, then, as a function of this of L, we expect there to be some optimum value of the Fischer information per time, beyond which there would be too much noise and the likelihood function would not be as informative. And so this optimum occurs when we choose L to be roughly 1 over this decay factor. So through many simulations, we arrived at a model for the performance of this algorithm. And some things that maybe there are a lot of constants here, which I don't want to draw too much attention to. But what I want to point out is that the performance of the model for the performance of this algorithm incorporates both this so-called shot noise limit scaling that was inherent to the VQE algorithm, but it will be reduced as the error on the quantum computer itself is reduced. And there's also this contribution from the so-called Heisenberg limit scaling, which was found in the quantum phase estimation algorithm. And so we view this model as describing the trade-off between the VQE type scaling and the quantum phase estimation type scaling. And the interpolation depends on the degree of error with each operation on the quantum computer. And so in doing some tests of this model, we find that it captures the simulations fairly well. So these solid lines are effectively the upper and lower bounds of this model. And the circles correspond to the average runtimes and target accuracies over, I think, like 100 different trials. And so the main thing to see here is that the simulation data fits well within the model in each of these cases. And this is over a range of different degrees of error on the quantum computer. So yeah, finally, to get back to this quantum advantage machine, we use this runtime model to get a sense of how we might expect this quantum advantage machine to perform. So we picture, for these problems of industrial relevance, you might need 100 qubits or more, and that the ansatz depths used are around 200. And so we'll consider the task of estimating the expectation value of a Pauli operator and carrying this out for several target accuracies. So the question is, as a function of the 2-qubit gate fidelities of the device, how long do we expect this enhanced sampling technique to take in order to achieve these target accuracies? And so just putting a plot down here, we find that as the 2-qubit gate fidelity is improved, getting closer to 1, there is a reduction in runtime afforded by the algorithm. But then at a certain point, the quantum computer becomes, for all intents and purposes, error-free. And so this brings us back into the quantum phase estimation scaling, where the improvements and the further improvements in the device don't yield reductions in the runtime. And so, this shows roughly that we can think that the VQE performance or the standard sampling performance is somewhere closer to this, the case where you would have error rates of 10 to the -5. And as the hardware is improving, there's a proportional reduction in the runtime that we can achieve by using these enhanced sampling techniques. So we expect that the quantum advantage machine will use techniques like this to overcome this measurement problem. And we look forward to a lot of work over the next few years in making these techniques work on real devices. So with that, I'll conclude. So we're finding that these enhanced sampling techniques are a promising antidote to the measurement problem. And the philosophy is that as the performance of the quantum computers increases, we can achieve a proportional time saving in carrying out this fundamental subroutine. And we started implementing this on today's quantum computers. And we're finding that in small instances, we can already outperform VQE. And I want to emphasize that this technique is useful before and into the regime of some quantum error correction or fault-tolerant quantum computing. So as an outlook, these techniques should find application in a number of different areas. So many quantum algorithms rely on this subroutine of statistical estimation. And we're also very interested to understand what implications this has for how to, for which hardware architectures stand to, basically which hardware architectures would carry out this subroutine best. So it might be that architectures that have slower quantum gates but have better fidelities are not necessarily best suited for reducing runtime of statistical estimation. And then lastly, I think a very important component of this technique is noise characterization and understanding or building more sophisticated models for the likelihood function by being informed by how noise is impacting the device. Okay, and so with that, thank you, and I'm happy to take some questions.
Okay, so now open to questions.
I have questions.
Hi, Lorenzo.
Hi, Peter. Thank you for the very clear talk. And I apologize if I might have nevertheless missed a couple of important points. One, I think you have alluded at the end, because you know that one of my interests has been into characterizing physical noise.
Mm-hmm.
And so I was wondering, it seems like the current input to the problem you have in terms of putting in the noise is very different from how I think about noise in terms of noise Hamiltonians or coherent errors, or like, yeah, this one. You have parameters which are in terms of probabilities, and, you know, do you have idea on how to fill slowly the gap between this description and the more physical description?
Yeah, okay, yeah, really good question. And maybe I should say that that's a question that we want to answer in more detail, and we're actively working on this. So I think the this expression is basically where the maybe the departure from what you might think of as like modeling noise enters. And so we're simply proposing a model for how noise might impact the relative likelihood of these binary outcomes, right? And the simplistic model is that with each Grover layer introduced, these likelihoods are squashed more and more towards a 50-50 outcome. You could think in the limit of far too deep quantum circuits, these Pauli measurements are just yielding, they're basically a random coin flip. And so a very simple model for how I would say maybe like a Krauss type model would yield this is if you imagine that each Grover iterate was modeled by a mixture of the completely depolarizing channel with the unitary itself. So that's one physical model, a very simplistic one, that would lead to this type of likelihood function. But of course, that shouldn't be the physical model that really describes the channel that this Grover iterate is implementing. So I think a very interesting question is how accurate is this noise model with respect to like how the device is really performing. So we might think that every single gate that's implemented adds an additional factor to this decay. But very likely, for example, if every single gate had some over rotation error, right? So no stochastic error, but every gate just had a over rotation error, so a unitary error. I would expect that this model would not capture well the effect of noise. But of course, there are some techniques for trying to convert this kind of bad unitary error into more stochastic error. So techniques like that could be very helpful in maybe like making this model more accurate. But yeah, I would say beyond that, this is very much an open question, and I think a really important one. Maybe the last thing that I'll say is probably you wouldn't want to go too crazy with modeling the likelihood function, because you still want this to be a tractable model in order to efficiently carry out inference. So I think there's a balance to strike there.
Yeah.
Yeah, great. I mean, maybe this is like the in my opinion, the most important follow-up question from this work.
And if I may, but this should be simple, you showed in your last plot how things would behave by changing, the 2-qubit gate fidelity as a metric for assessing improving quality. Where should I put or think about? You talked about the measurement problem in terms of like the the precision improvement that is needed, but what about the infidelity of the measurement itself? Like often experimentalists, I have measurement errors like a flaw or those kind of things, which are limiting factors even more, for instance, in trapped ions, that the fidelities of gates themselves.
That's okay. Yeah, great question. So yeah, maybe here. Okay, so yeah, the way that this model is taking into account, maybe you would call it like state preparation and measurement error, is this enters down
All
here in
in
the denominator.
Okay, it's all there.
And in the likelihood function, right, this is coming into this spam error. And so yeah, I think this could be pretty bad, especially with these poly measurements where every single qubit is measured. You might expect this spam error to be like exponentially suppressed in the number of qubits. So yeah, this could be okay, but I will say that this turns out to be independent. The spam error turns out to be independent of the optimal number of layers to use, because it remains fixed as you add more Grover iterates. So yeah, definitely it reduces the performance, right, as this model includes, but it just it doesn't change the it doesn't impact the the choice of the number of Grover iterates.
Thank you, Peter. I had missed that. Thanks.
And maybe a last thing is that, right, this issue is still present for standard sampling, just as much as it is for
Yeah,
dynamic sampling.
yeah.
Yeah, great question.
Okay, any other questions?
So you mentioned using this method in a fault-tolerant regime towards the end.
Yeah.
Have you looked at what the runtimes would be like under those assumptions?
Yes. Okay. Yeah. Excellent question. And yeah, maybe you might have caught that, right, looking at these 2 qubit gate fidelities, it's very unlikely that you'll be able to implement these with like physical gates, right? These are very much in the regime of what you would expect logical gates to be achieving. So this this plot here ignores the overhead of quantum error correction. And so, with quantum error correction, taking like the surface code, we can effectively think that, maybe as you increase the distance of the code, there's a proportional cost in time, but an exponential reduction in the error rates. And so if you were to include that in this plot, we've been looking at these plots as well, what you find is that due to this this time overhead, the plots will like decrease, and then reach a minimum, and then they'll start to increase. So this reveals basically a point at which further quantum error correction is not helping the performance of the algorithm. So yeah, one thing that I'm very interested in with this is I think this shines some light on the question of how much error correction would be needed for a given application. Yeah, excellent question, John. And does that answer your question?
Yeah, yep, thank you.
Any other questions? Okay, so let's thank Peter Johnson one more time.
Thank you all for joining. Thanks for your time. Thanks for the questions.